All right, well, we're going to get started. Hopefully the last few people will get here shortly. Join the class. So today we will be doing some practice with our new chi-square statistic and looking at the things that we need to be able to do to be able to use that. So we have a Desmos activity that we'll do today to hopefully help us practice. So I'm going to put the link for this activity in the chat to make it easier for you all to get to. And my chat decides to go, there it is. All right, so there you go. So the link should be in there. You guys are restricted to the first screen on this activity for right now. It's just a check-in screen just to see how y'all are doing. You can also, if you don't want to do the link, you can go to student.desmos.com, go into our period 1 class, and the activity should be there. The AP Stats 11.1 activity. Alrighty. Good morning. Alright, we are going to get started. So the first few slides, as I've done previously, they're going to be kind of just review of the things we saw yesterday, so that we're all kind of like back into it, and then we'll get some questions and practice. Oops, I don't want to do that. I want to do that one. There we go. All right, and I need to do this. Make more sense. All right, so first, just what is our chi-square test for goodness of fit? Right, the chi-square test for goodness of fit allows us to test a claim about a distribution of categorical data. This is different than the previous inference methods we have used because it allows for testing the evidence for or against an entire distribution rather than just one value within the distribution. Right, so rather than testing each value in a categorical distribution against an alternative, which would be very time consuming, we can test the whole distribution with the chi-square test for goodness of fit. So that's the big idea here. All right, this is our chi-square test statistic, which we will use today. Right, our chi-square test statistic is a measure of how far the observed counts are from the expected counts. The formula for the statistic is chi-squared equals the sum of each observed count minus its expected squared divided by the expected, or the sum is over all possible values of the categorical variable. Right. And we have our chi-square distributions. This is a little picture of our chi-square distribution. There's a few examples showing that right skewed distribution there on the left. Our chi-square. Right. And writing turned out really small. All right, but the chi-square distributions are a family of density curves that take only non-negative values and are skewed to the right. Particular chi-square distribution is specified by giving the degrees of freedom. Right, the chi-square test for goodness of fit uses the chi-square distribution with degrees of freedom equal to the number of categories minus 1. It does not have anything to do with our sample size. Some things to remember here: as the degrees of freedom increase, the density curves become less skewed and larger values become more probable, which essentially means the more categories we have, the more acceptable it kind of becomes to have larger differences, so to say. Right. The mean for a particular chi-square distribution is equal to its degrees of freedom. Right? And for degrees of freedom greater than 2, the mode or the peak of the chi-square density curve is at degrees of freedom minus 2. Right? Those are just some things to be aware of with our chi-square distributions. Okay, and again, we have our conditions for performing a chi-square test for goodness of fit. It is our random 10% and large counts conditions. The random and 10% are the same as we've seen for everything else that we've done inference on. Large counts is slightly different than the large counts we saw for proportions, and that this large counts is having all expected counts are at least 5. Right? Previously, when dealing with proportions, we needed our basically our expected amount of successes and failures to be at least 10. Now we're going down to 5, but each of those expected counts must be at least 5. Okay. And then lastly, this is entirely too small for me to read from here, but this is just that basically summing of what we must do to do a chi-square test for goodness of fit. Right? We have to check our conditions. If the conditions are met, we write our hypotheses. Right? State what we're going to do. We need a null hypothesis that says the proposed distribution is correct, an alternative that says the proposed distribution is incorrect. Right? And then we have to find our expected values for each category, compare those to our observed values using our chi-square statistic, and then find our p-value based on that statistic using table C, and compare that p-value to a significance level. And so it's a lot of the same steps that we've done previously, except now we're using the chi-square statistic in table C. All right. Are there any questions before we move on to the questions part of this? Is there anything I can clarify? All right. And we will move on. All right, so our first part here is one of the first things that we have to do when we're doing a chi-square test for goodness of fit is compute our expected counts. We may already know the observed counts, but we need the expected counts to be able to proceed. Right, so in this context, Jenny made a 6-sided die in ceramics class and rolled it 60 times to test if each side was equally likely to show up on top. Assuming that her die is fair, calculate the expected counts for each possible outcome. Right, and you just simply need to type the number into here, and I've got it set up so if you put the wrong number in, it tells you that it's wrong. Right, if you put the correct number in, you'll get a check mark saying that it is correct. All right. So take the next few minutes and fill in the table. All right. So our time for that one. So it looks like most of you that worked on this one were able to either get it correct first time or figure out how to get it correct, just based on the check marks I see on my screen. All right. With this context, what's the null hypothesis essentially? What is the claim? What are we testing? What are we hoping to find out?
The expected count on the roll of the dice.
We want the expected count, but what piece of information in the context tells us how to calculate it? Because we're not given any proportions.
If you're doing 60 rolls and there's only 6 sets of the dice, there's only really that little part right there that tells.
Okay.
The expected count for.
All right, so you just did 60 divided by 6. But so that's one way to do it, all right? However, the key thing here is that we're looking at things that are supposedly equally likely. Each side has the same probability of ending up on top. Right? We could theoretically have a die that is not fair, that has a weight on one side of it, and that's going to cause the opposite side to show up on top more times than the rest. All right, it would be unfair. Right? And we have our expected count to test against the dice being fair, which says each side should be equally likely which means there's a 1 in 6 chance, 1/6 probability of each side landing on top. So even though the proportion of probability wasn't given in our context, yes, and Caesar said it here too, assuming that it was fair, right? That's a key thing that we all read and we get it, but if you were asked to put it into words, could be tough, right? What exactly are they asking for? How are we gonna put this into a null hypothesis if we need to, right? So we have to be able to kind of translate the context in that way. That's why I wanted to pause and make a point of it. Is there anything I can clarify on that? Solid. All right. So that leads us to the next. Where did my mouse go? There we go. So we'll open it up to our next question, and we have expected counts again. Similar type of calculation, same kind of table we're looking at here, but we have a new context. Right? A company claims that each batch of its deluxe mixed nuts contains 52% cashews, 27% almonds, 13% macadamia nuts, and 8% Brazil nuts. To test this claim, a quality control inspector takes a random sample of 150 nuts from the latest batch. You might need a calculator for this, and you might need a piece of scratch paper to write down your results. That's up to you if you need to do those things. But in this case, each of these things are not equally likely. Okay, so keep that in mind. All right, so for this one, looks like we're a little mixed on being able to get it correct or not, which is totally okay. Look at this. So one thing to keep in mind is when we're dealing with expected counts, it's okay to have a decimal. We don't need whole numbers for expected counts. So if you get a decimal, that's fine. That's the expected count, right? The other thing is to make sure that you're using the sample size times the probability of that nut being there, right? So for this one, we should have had 78 cashews, 40.5 almonds, 19.5 macadamias, and 12 Brazil nuts. Again, this is self-checking, so that's kind of nice. You can see your instant feedback. All right. And again, each of these was found by saying 150 times 0.52, 150 times 0.27, 150 times 0.13, 150 times 0.08. Make sure your decimal is in the right place when you're converting percentages to decimals. So anything I can clarify on this one? In computing our expected counts when it's not equally likely events. Okay. So next, unfortunately, this one is not self-checking, right? We're doing the same context, but now we're going to state the appropriate hypotheses for performing a test of the company's claim. You need to write a null hypothesis and an alternative hypothesis. And once again, I'll say it's easier to write that as a couple of sentences rather than trying to have all of your parameters defined. Okay, so this one seems to be a little trickier for everybody, and that's okay. We're still learning this, we're practicing. That's what we're doing this today. So again, I suggest writing this as statements rather than using parameters, like saying P of cashews or P of almond equals this or that or the other thing, because there's just more things for you to be judged on, to be honest. Right? There's more things to write incorrectly and not define properly and those types of things. writing it as a statement gives you a little bit more wiggle room, I guess. All right. Essentially, our null hypothesis is that the stated distribution, the company's stated distribution of types of nuts in their deluxe mixed nuts is correct. And the alternative is that the company's stated distribution of types of nuts in its deluxe mixed nuts is not correct. We can have our null and alternative hypothesis stated as simply as that. What they say is true, what they say is not true, in a nutshell. But nuts, nutshell. All right, I got jokes. All right, so again, we want to try and make these hypotheses kind of as simple as possible, but still say what we're testing. The more detail you start adding when it's not needed, the more things you can be judged on in an AP exam, and the more things you could lose credit for, if you want to think of it that way. All right. Is there anything I can clarify about our hypotheses? Any questions? So now we have a lot of data to use, and we want to calculate the chi-square statistic. Chi-square statistic, again, is a single number that will be a decimal. Right, and we're going to use our table below with our observed and expected counts to help calculate our chi-square statistic for our distribution. And remember, if you need to, slide 3 here has our chi-square statistic formula. You're most likely going to need a calculator or some scratch paper to work this out. All right, so let's go over this one. So here, let's do this. Let's see if the calculator wants to start up. All right. Oh, I didn't want that. There we go. All right, so let's use the calculator here. When we're calculating our chi-square statistic, we should have, in this case, we have 4 categories for this categorical variable. We should have 4 fractions we're adding together. If you calculate each one individually, depending on how you round those results, you could throw off your answer a little bit from what it maybe should be. So the best way to do this is to do all of it in one shot in your calculator. Okay, so in this case, we're going to use our little fraction thing, which we can do alpha y equals, and then hit enter, and we get a fraction. I will do the first one. We need parentheses, 83 minus 78 squared divided by 78. Okay, so that was our observed minus expected squared divided by the expected, plus, do our next one, (29 minus 40.5 squared divided by 40.5. Oops. That was a mistake. That's easy fix. Get to the end. There it is. Close. All right, and so knowing how to use your calculator can be very beneficial in this case, because I can type this in exactly the way I would have written it, which helps in making sure things go well. All right. And we get our last term. All right, and we get 6.59876, blah, 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 big old decimal. All right, now how you round this decimal needs to be done correctly. The number of decimal places and things, usually we're not going to keep any more than like 3 decimal places for our results. If I round this to 3 decimal places, I should round to 6.599. Because the third decimal is 8, but the number to the right of it is greater than 5, so I round up 6.599. If I try to round any other place, it rounds the whole thing down to 6.6. Right, if I want to round to 2 decimal places, 9 rounds up to 10, which makes it 6.6. If I want to round to 1 decimal place, 5 rounds up to 0.6 because 9 is to the right of it. All right, so make sure you're rounding correctly. And try to make sure you don't round too early. Right? Rounding each of those fractions could result in getting a slightly different result. Okay. Is there anything I can clarify about this calculation and how we did it? All right. So then we'll move on. All right, and our next one here, large counts and degrees of freedom. Same context. Confirm that the expected counts are large enough to use a chi-square distribution to calculate the p-value. So it's either yes or no. That first submit button goes with answering yes or no. Submit your answer, it'll tell you if you're right or wrong. Right? And then what degrees of freedom should you use? Based on what we know about our chi-square test for goodness of fit. What is our degrees of freedom? Alrighty. So for this one, is large counts condition met? Yes. Yes, it is. All of our expected counts are at least 5, so we're good on that. Right. Degrees of freedom. We have 4 categories for our categorical variable of type of nut, right? You do almonds, cashews, macadamia, or Brazil. Degrees of freedom for a chi-square test for goodness of fit is number of categories minus 1, which means we have degrees of freedom equaling 3. Okay. Is there anything I can clarify about our large counts and degrees of freedom? All right, so same exact content again. Now that conditions have been met, you have the value of the test statistic, right? And you know the degrees of freedom. We need to use table C to find the range of the p-value. So please type that p-value range in the box below. You have a link to the formulas and tables right here. So you can get to table C. And then what conclusion would you draw about the company's claim distribution for its deluxe mixed nuts? Please justify your answer. Remember that since a significance level was not given, you should use alpha equaling 0.05. So we'll take a few minutes here to answer these questions. All right, so here we go. We're going to talk about this one. I know that some of you are right in the middle of trying to write out your answers for both of these things. That's okay. So if we go to our formulas and tables, let's go, bam. And we go to the very last table, which is table C, and we zoom in. We have our degrees of freedom of 3, right? And we follow that over till right here, 6.25, 7.81. Right? We stopped there because our chi-square statistic was 6.599, 6.6, however you rounded it, right? It's between those two values. Then very similar to how we use table B to find a p-value, we follow this back up to the top of the table where we have our tail probability, which is our p-value. And that says that our p-value has to be between 0.05 and 0.1. Right? And again, it is proper to list or write the smaller value first of 0.05 when you're talking about a range of values. Right, 0.05 is smaller than 0.1, so we would say p-value is between 0.05 and 0.1. If we write it as an inequality, which we'll show, we could say that 0.05 less than the p-value and 0.10. I have too many zeros. There. All right. So we can write it as an inequality here, and that answers the question if I write it as an inequality. Or you can write it out and say the p-value is between 0.05 and 0.1. All right. And so that's our p-value using table C. And our conclusion, you know, since our p-value is greater than 0.05, because we know it's greater than 0.05 but less than 0.1, we fail to reject the null hypothesis. Right? That means we do not have convincing evidence that the distribution of types of nuts in their deluxe nut mix is incorrect. That's what we do not have evidence for. Okay. Right, and so you can say, yeah, we don't have enough evidence that the company's claim is incorrect. That's fine to say. On the AP exam, you want to be as specific as possible when you write your conclusion. You're going to feel like you're being redundant. You're going to be saying like the company's claim that the distribution of the types of nut in there, It seems ridiculous, but you're giving exact kind of information about your context, and they want that in this scenario, right? So, awesome. Any questions? Anything to clarify on that? All right, we're gonna go to our last little thing here, which was the part that was missing from yesterday's lesson about our follow-up analysis. This is the blurb on follow-up analysis. When sample data lead to a statistically significant result, which we did not have in our nut example, right? We can conclude that our variable has a distribution different from the one stated. When this happens, we start by examining which categories of variables show large deviations between the observed and expected counts. Then look at the individual terms from our observed minus expected squared divided by expected that are added together to produce the test statistic chi-squared. These components show which terms contribute most to the chi-squared statistic. Right, determining which component contributed the most to the chi-squared statistic will allow us to get an idea of which categories have incorrect hypothesized values. Right, and so our example here goes back to the hockey problem that we saw yesterday, which I've provided all the stuff here. So if we're looking at this context, which I can now move you to, which component contributed most to the chi-square statistic? And we have our 4 categories of the 4 quarters of the year and how many NHL players were born in each of those quarters versus the expected, and then we have the observed minus expected squared divided by expected value for each of those components. Right? Which component contributed most to the chi-square statistic? And this is essentially just looking at the numbers. Which is the biggest number? Right? And we see that the largest number is the January through March value, right? 7.2. It's greater than the other 3. Right? We can then make a kind of like a next step of the conclusion and say, you know, this further supports that guy's claim who wrote this thing, that the book that they were talking about in this example, that the players who are born earlier in the year have an advantage, right? They tend to be more successful when it comes to making it to the NHL, and that's supported with our data. It doesn't prove that, but it's support for that claim. Right. So not going to have you guys necessarily do this question. I had it set up, but it could, but I don't know if we need to. Is there anything I can clarify on that follow-up analysis? That's essentially what it is. Which thing contributed the most to our chi-square statistic? All right. I'm going to stop sharing my screen. Okay, so that was our practice for getting a little bit more comfortable with our chi-square statistic and tests and our test for goodness of fit. I'm hoping to have our practice problem set ready today or tomorrow for section 11.1, and all the other stuff ready by the end of the week. Hopefully I can do that. Other than that, I hope we'll see you next week. We'll be doing section 11.2. 11.2 is a little bit more robust than 11.1, so we'll see if we can do it in, within next week, but that all depends. So have a great rest of your day, and I will see you all next week.